Thank you all for coming to this presentation. I would like to introduce Yagub Aliyev from the ADA University presenting interception curves. So I pass it on to you now.
Thank you very much. Thank you for the invitation. It is very early here, so it is 5:30 a.m. in Baku. So I'm sorry if I will make any mistake because of this unusual time. This is not a usual time for me to do mathematics or present. Okay, our topic is interception curves. I will discuss this name by the end of this presentation. Why interception curves at the end. For now, let us start with something simple. Everyone in this room probably knows about this limit. The first thing that undergraduate student learns, one of the first things in calculus course, is this limit. In regions of the world influenced by Soviet mathematics, we call this remarkable limit, first remarkable limit, limit of sine theta over theta when theta goes to 0 is equal to 1. How do you prove this limit? You probably saw this proof in various textbooks, calculus textbooks. The idea is that theta is between sine theta and tangent theta. And in the next step, you divide this by sine theta, and then use sandwich theorem, which is by then is already covered. What does it mean? Where does this inequality come from? Sine theta less than tangent theta. It is a geometric fact, follows from a geometric fact. It follows from the fact that area of triangle AOB is less than area of sector AOB, which is less than area of triangle COB, which is obvious, because each of these is included in the next one. So it follows from this inequality. Now, let us look at this part of the inequality, theta less than tangent theta. What does it mean from geometric standpoint? Theta less than tangent theta means that this green arc length is less than this black part of tangent line. Okay, so we are mathematicians. We ask questions. So we can ask whether it is possible to replace this unit circle with another smooth curve passing through the point B again, such that now the length of the curve AB is not less than this black tangent line segment, but equal to it. So the question is to change this green circle with another curve so that the length of AB arc is now equal to BC. Is there such a curve? Now, you know formula for the length of a curve in polar coordinates. It is like this: integral from 0 theta square root of r squared plus r prime squared d theta. Since we want this length to be equal to the length of the tangent part, it should be equal to tangent theta. We obtained an integral equation. If we will take it as derivative, we will easily get this differential equation. Now, this differential equation is nonlinear, so it is not easy to solve it. One can try to find approximate solution. You can find the solutions as series. using Maple, one can find these solutions, R1 and R2 for this solution, for this equation. The boundary condition is that it starts from 1. So R0 is 1. We obtain two series solutions. The first one is, of course, 1 over cosine theta, the original line, and the other one is is a new solution, which gives us this approximate shape. This diverges from the line because we truncated it here somewhere. So this is not the whole series, only the first 3 non-zero terms. So we obtain it not a straight line, but something which diverges from the straight line a little bit. Okay, so this was good to find approximate shape of this curve. You can get more and more accuracy if you will take more terms of this series. Maybe there is an exact solution for this. Actually, yes, it is possible to find something like exact solution by using the methods proposed in this encyclopedic book by Kamke. I don't know if it is an English translation, probably yes. This is encyclopedic book in German. It appeared in 2 volumes. So in that book, it is for this type of equations where our fx is 1 over cosine squared x, it is recommended to use some substitutions to simplify it. First of all, it was noted that to solve this equation, one can transform it into first type Abel equation. First type Abel's equation using this substitution, r equals f times sine of ux. And then using ux equals tangent y, you can transform it into Abel's equation. This equation was also mentioned in the paper by Wilder, which I will mention again in the coming slides. And solutions in quadratures are given in Zbornik. Unfortunately, I don't have access to this paper. I couldn't find it on internet. So they are mentioned in those papers, and there is a solution in quadratures, which you will see here anyway. So how can we solve this problem exactly? So in Kamke, it is mentioned that you can use this substitution to obtain this equation, and then differentiating and excluding y and y prime, you will get this equation. There are 5 steps, so I will go faster through them. In the next step, you need to use these substitutions to get Abel's equation. In the next step, this substitution to obtain this Abel's equation. In the next step, this to obtain this equation, and the final step, using this substitution to obtain this linear equation, which we can solve using quadratures. Still, even though you can use quadratures to solve this linear equation, the expression in the final step will involve elliptic integrals. And going back through all the steps to find the solution in terms of y and x will be very difficult, complicated expression. So I didn't even try to do this. So about Wilder's paper, he asked this interesting question. Let me read this question. This question was asked by some doubtless well-meaning freshman to Professor Brown. An automobile moves along a straight road with a constant speed, while a man in a field beside the road walks with a constant speed along such a path as to always keep a tree between him and an automobile and the automobile. Determine his path. So if you will look closely, you can easily see that this question is similar to the question that we discussed here. There are other papers which solved similar questions. A recent one I found in Mathematics magazine. You can see it here. It appeared in 1994. The name of the paper is The Hiding Path by Herbert Bailey, which also asks a similar problem. A fox is initially B units due south of a tree, and a rabbit is initially C units due north of the tree. The fox runs due west along a straight line path with constant speed v. The rabbit also runs at constant speed v and must remain hidden from the sight of the fox by keeping fox, tree, and rabbit on a straight line. So you can check that it is equivalent to the question that we discussed, or this Wilder paper discusses. Now, this paper doesn't refer to this paper. So many people discovered and rediscovered the same problem and tried to work on it. In all these papers, authors mentioned the difficulty of the problem, which is indeed correct. So at the end of his paper, Wilder writes that if the reader will take the trouble to finish up any or all of the methods of the solution suggested, he will see why the formal solution is a useless form of answer to our problem. We refrain from writing them out, they would take too much space. The nonlinear differential equation that we saw before is very difficult to solve, analyze using traditional methods. And in these two papers that I found, it is mentioned that the final solution will be difficult to find. Maybe approximate solutions. We already saw one approximate solution using series. There is another attempt, another approach to approximate solution. So one can think like this. What are we trying to do? We want to find a curve such that its length is always equal to this line segment for any angle. But we can do this using Euclidean constructions, compass and straight edge constructions. Just take this as equal to this, drawing this compass, and then this equal to this. A1, A2 is equal to C1, C2, then A2, A3 is equal to C2, C3, and then A3, A4 using C3, C4. All of these are done using compass, as you can see here. So we achieved our objective. So there is a broken line, which is approximation of our curve, which whose length is equal to this. By taking the angle between these lines emanating from O, by making the angle between these lines smaller, you can get better and better approximations of this curve. This here I described how these constructions work, which is not difficult. Each time you take the radius equal to this part on the original straight line through B. And if you will increase, you will get a good approximation of increase the number of emanating lines, you will get a good approximation of this curve. So when you look at this broken line from here, you don't see any broken line, you see just a curve. So it is nice approximation of this curve. Of course, this idea can be generalized for other curves and not just straight line. You can take any curve and apply that same procedure. So BA1 is equal to BC1, A1, A2 is C1, C2, A2, A3 is C2, C3, A3, A4 is C3, C4, and so on. You can draw for any given curve, you can find another curve which has the property that its length between two lines forming an angle at O is equal to the length of the curve. We call this transformation of a curve interception. The reason for the name later. Again, the differential equation involved in this change is this. So the given function R and the new function, red one, will be the two solutions of this nonlinear differential equation. R is unknown function, phi is given function. As the case phi theta equals 1 over cosine theta before suggests, it is not always possible to do this analytically, the solution. So it is again reasonable to have an approximate method that I demonstrated here. Okay, one can do those, construct this polygon as I described it. So I skip this. We call this process of constructing a new curve interception. So I have shown you examples where one of the functions is known, the other one is difficult to find exactly, but I tried to find also examples where both of the curves, both the given one and the new one, are explicitly written functions. I tried to find some examples and I used this formula for it. So if you have two solutions R1 and R2 satisfying that differential equation, then this should be true. But if you will introduce 2x and 2y, which are unrelated to original xy, they are both functions, x and y, of theta, then you end up with this equality, which can be written like this or like this. And this is a nice thing. You can find elementary functions satisfying this. I will show you some examples of functions x and y of theta, which satisfy this nice equality. And the basic example would be two circles, because ln sine theta prime is -1 over ln cosine theta, which is easy to check. So these two circles indeed satisfy. So if you would take this curve as granted, the interception curve will be this. I found also other examples. When x is theta and y is minus theta squared over 2, the curves look like this. So they enjoy the property that whenever you draw a straight line from origin, the part of the curves are equal to each other. Okay, interesting. More examples: x equals square root of theta, then y is equal to minus e to the minus theta squared. More examples. This time the curves do not intersect, just go to infinity, and x equals 1 over square root of theta and y equals e to the theta squared. Of course, this idea can also be generalized to the cases when the initial point is not on the curve. So if you start from a point different from the point of a curve, then you will obtain again another curve. The idea is the same. We call also this interception. So here's my conclusion, but I will show you some pictures about maybe possible applications of interception. So the study of curves and their properties has long history dating back to the time of ancient Greeks. Modern mathematics applied the theory of curves with analytical tools and abstract viewpoint. In the current presentation, I studied one interesting curve in detail. Its approximate shape was drawn as a broken line. This construction I did using GeoGebra. And then we generalized this idea. We named this as interception. And some elementary function examples for this interception was given. So where does this name come from? There is a real life interception. This image shows this real life interception. Rockets can be intercepted with another rocket. I found this reference, very old book, old paper from 1963, Interception of High-Speed Target by Beam Rider Missile. So in that paper, that same differential equation that I mentioned was studied. that r squared plus r prime squared equals 1 over cosine to the 4. So this has some real life applications. Is this interception important? Probably everyone here will agree that it is very important for security of countries. That's how intercepted rockets look like. If you intercept them, they are just a chunk of metals. But what happens when you don't intercept them? It looks like this. So it is important. It can have some important applications. Okay, I recently completed this paper of mine, submitted to the journal Symmetry, and it was accepted. I found some parametric representations for this curve, which is here, is shown in blue. This curve enjoys some interesting geometric properties which were not noticed before. I proved them. Also, there are some connections with Leibniz-Cut functions and Leibniz-Cut constants. And this can also be compared with with classical pursuit curve, which was mentioned today at the beginning of the conference by some of the presenters. So original pursuit curve was introduced, I think, in 1800s by French mathematician Bouguer. And the idea behind pursuit curve is that the pursuer always directed towards evader. But here in the interception curve, the idea is that pursuer tries to be on the same line with evader while moving with the same speed. Okay, and it can be shown that this strategy of being on the same straight line with the evader is a better strategy. So the pursuer approaches evader better if it follows this strategy, not the strategy in pursuit curve. In pursuit curve, the closest that you can get to the evader is 0.5. But in interception curve, the closest is much less than 0.5. It is 0.3 something. And this constant is related to Leibniz-Cut constants, namely second Leibniz-Cut constant. I also tried to generalize this question for a sphere, and many interesting results came out of this. So the function is related to good Riemannian function, and this curve also enjoys many interesting properties. For example, one of which I can mention here, if you draw this interception curve on sphere, similar problem. So pursuer starts from here, evader starts from here, it goes along equator. Pursuer always tries to stay on the same great circle, which passes through the North Pole and the evader point, which moves here. And the point P has the same speed as the point Q. So you obtain this spiral-shaped curve, and this curve has many interesting properties, one of which I can show here. The angle arcs PT plus TQ is always pi over 2. Very surprising result. And there are other geometric properties that I can mention. They will appear in symmetry, special issue of differential geometry. The paper that already appeared, I can put it in the chat. And if you have any questions, I'm ready to answer. This paper appeared last year. Thank you for your attention.
Thank you. Yeah. Can you hear me?
Yes, I can hear you.
Anyway, thank you. That was fascinating and clearly has taken a great deal of perseverance and work. And boy, the results are stunning. Thank you. Wow.
This is the last talk in today's conference. Probably not many people left here.
Right, but thank you for getting up early so that you could be included in the program. That was much
Yes.
appreciated by me.
Thank you. You're welcome. Usually we mathematicians, when we prove our theorems, we don't think much about applications. But there are probably some applications, some of which we can be found in a few years or maybe 100 years or so.
Wow, I like the last comment in the chat. It gives students a reason to care about a topic that we often see as pure geometry. So you don't see so many applications of pure geometry other than beautiful art, but this one is certainly topical today, and I appreciate understanding it better.
Thank you so much for the presentation.
Thank you again very much.
Thank you all.